And welcome also to this second day after Catherine's very interesting talk. We will go through the poster session. So we decided since last year that it was very nice to offer the poster presenters to actually come on stage and tell us a few words about why the posters are interested and why we should go and have a look at them and eventually also vote for them. So I invite you all to come to this evening poster session at 7 p.m. and also to please look at the posters and vote for them, because we will have we will give an award to the 3 best posters of PASC17 tomorrow. I invite all the poster presenters to please come on stage. Whoever is in the audience, all of you, because otherwise we will not have time to change and whatever. We the order is this: we will start with chemistry and materials, then climate and weather, computer science and applied mathematics, emerging domains in HPC and engineering, life sciences and physics. If after you have presented your poster you want to go down the stage, please do, but without creating any chaos. So either you can do it quietly or stay on stage until we finish. It will not be too long. So I will call, of course, your name. You will have 40 seconds to present the poster, and I will be very strict. So if you exceed your time, I will simply take the microphone from you. I will be the tough woman in the room. So, okay. So let's start with posters in chemistry and materials. And the first poster is Ricardo Inocente Malini, a molecular dynamics study of the thermodynamics of attachment of saccharides to halloysides. Is it here? Yep. Please go there.
Good morning, everyone. My name is Ricardo, and my poster will be about the interaction between saccharides and halloysite structures. Halloysites are tubular aluminosilicates, which are often used as reinforcements or drug delivery systems within polysaccharide films. However, their interaction with polysaccharides at the interface has not been investigated. Here we use molecular dynamics to understand the binding motives, the free energy of interaction, entropy and enthalpy to understand the driving force behind the binding. This will help design better composite materials in the future.
Thank you. So second poster is Yoshitaka Tateyama from NIMS, first principles study on interfaces between sulfide electrolyte and oxide cathode in all solid state battery. Yes. Please.
Good morning, everyone. My name is Yoshitaka from Japan. Oops. And, okay. Actually,
okay, you start on a different poster. I'm sorry. It doesn't...
Right. Okay. Anyway, the interfaces are really complex and have been hard to investigate so far. But nowadays,
yeah, please continue.
It's quite accessible by the high-performance computing and the machine learning techniques. So we addressed, in this poster works, we addressed solid-solid interfaces in lithium-ion batteries. And more importantly, actually I'm organizing 2 symposia. It is chemistry and materials categories, which regarding the interfaces and the fast principle large-scale calculations, which actually mini symposia 24 and 46. If you have time, please visit. Thank you.
You're welcome. Please don't touch the mute button, otherwise nobody will hear you. So next poster is Felix Musil from FFL, mapping and classifying molecules from a high throughput structural database. Please.
Good morning. There is no mute. Okay. So it is often in computational material science and chemistry, we often produce thousands of new hypothetical atomic structures, and it can be very cumbersome to and time-consuming to inspect them all. So we present in this poster a set of machine learning techniques to represent the structural relationship between the members of a database, of this database. So what you can see here is the result of this representation on a small set.
Thank you. I'm sorry. So they told me to simply come at the podium and talk from these microphones. So next poster is Giuseppe Fisicaro, University of Basel, soft sphere continuum solvation in electronic structure calculations. Please.
Thank you. So good morning. In my poster, I will give you details of the implicit solvation model we developed to include complex wet environments in electronic structure calculation. In particular, details of the continuum permittivity, three-dimensional continuum permittivity to map the electric cavity. Then details of the solver for the generalized Poisson equation by means of a preconditioned and conjugate gradient algorithm, and benchmark of the solvation model on a collection of free solvation energy for a small molecule, and for solid-liquid interface by means of contact angles measurements. Thank you.
Thank you. Next one is Oliviero Andreusi, Università della Svizzera Italiana, solvent-aware interfaces in continuum solvation, please.
So this is again about continuum solvation. So it's a multi-scale model where you have a part of the system which is treated atomistically and part of the system which is treated as a continuum. A key ingredient is the interface, how you define the boundary between the continuum and the atomistic regions. And in general, you exploit the degrees of freedom of the solute, but you need this boundary to represent the part that is not accessible to the solvent. And so there is some tricky situations in which you have, for example, pockets of continuums which are smaller than solvent molecules, and this is a way to avoid these artifacts.
Thank you very much. So that was all for chemistry and materials. Now we have the climate and weather. So the first poster is Willem de Koninck, ECMWF, ESCAPE, Accelerating Extreme Scale Numerical Weather Prediction. Please.
Good morning. ESCAPE is a project for numerical weather prediction and climate, and it combines scientific and computer science expertise. It involves many numerical weather prediction centers, hardware, HPC, and university. The idea is to extract mini applications from our weather model and look at them in isolation, run them, and optimize them, port them to different hardware. And in the end, the idea is to reassemble a model. One of the cornerstones for this is Atlas library to help in new numerical developments. And if you want to know more about the way forward, please come see the poster.
Thank you very much. Next one is Mauro Bianco from CSCS, Grid Tools, a C++ library for computations on grid. Please.
So the Grid Tools is a library to compute on grids, and you can express your numerics in a grid agnostic way, and it will run on CPUs, on GPUs, and also on other architectures. So even if you are not in climate and weather, pay a visit there because it might be actually interesting to you. And Mauro Bianco and I approve this message.
Thank you. Thank you, Mauro. Okay, the next poster is Pascal Spöri, C2SM ETH Zurich, high-performance C++ in weather prediction, challenges, achievements, and future models.
Yeah, so I discussed the C++ port of the Cosmo Fortran dynamical core to a performance portable version. So this code is running daily on the Meteor Swiss supercomputer at CSCS. So if you open the Meteor Swiss app, you can see the results of these computations. Analyzing the results, we're also able to give suggestions for future models. And so basically the 4 continuous papers also reference this source code when they say C++ and dynamical core. And so if you want to know more about our challenges and how this thing works, come visit me at the poster.
Thank you. Yeah, better. So next poster is Hannes Burg, CSCS, large-scale climate simulations with Cosmo.
Thanks, Pascal, for the nice introduction to our poster. What did we do? We took the Cosmo GPU version and run this regional model at global scale at very high resolution of 1 kilometer. To run 1 kilometer global, you need a fast computer. Luckily, we have PIT-Steint, and we run this code on the full PIT-Steint machine. Additionally, we discuss a performance model, and we propose a metric which focuses on data locality instead of pure memory bandwidth.
Thank you very much. So next poster will be Christophe Charpillot, I hope it's correct, Meteo Suisse, reproducible climate and weather simulations, an application on, an application to the Cosmo model, sorry.
So hi, I'm Christophe Charpillot. I'm working at Meteo Suisse for the CIRCLIM project. And in this poster, I present what we did to make the Cosmo weather and climate model reproducible. And by reproducible, we mean that we find a setup in which the model produces the exact same numerical result when executed on a GPU and a CPU. So if you want to have a look at our current results, or if you have any knowledge or experience with the reproducible computation, I'd be happy to discuss and share with you. Thank you.
Thank you. Next poster is Marco Alemanno, Comet, use of hybrid supercomputing architectures for numerical weather prediction models, please.
Good morning, everyone. In my poster, you can see some important results about some experiments we performed on our GPU supercomputers. In particular, we performed these experiments by running a particular GPU version of our weather forecasting model, Cosmo model. And in this poster, you can see from this experiment we performed, we saw that there is a significant speed up in lead time by exploding GPU version.
Okay, thank you. They come to your poster to know more, don't worry. Posters in computer science and applied mathematics is next. So the first one is Gabriele Torre, FHNW, and novel and efficient compressed algorithms for non-negative matrix factorization. Please.
Thank you. Hello, my name is Gabriele Torre, and our poster is about a new data decomposition technique for non-negative data sets. Essentially, it exploits random projection-based data compression within block coordinate descent optimization technique for the solution of non-negative matrix factorization problem. Our method is essentially associated to lower numerical complexity, lower memory consumption while preserving the same accuracy of the state-of-the-art NMF algorithm. Thank you.
Thank you very much. Next one is Carla Morris, Sandia, a resilient ULF MMPI-based PDE solver, performance scaling and energy analysis. Please.
This work is done in collaboration with Sandia National Labs, Lawrence Berkeley, and Duke University. We present a resilient domain decomposition preconditioner for PDEs. We reformulate the PDE as a sampling problem, followed by a solution update through manipulation of data that is resilient to both SDC and hard faults. We show the scalability of the solver for runs that are both nominal and with faults. And then we do energy analysis that shows how we can save energy for this algorithm.
Thank you very much. Next one is Marco Favino, again USI, AV Flow, a software library for fluid structure interaction problems based on variational transfer immerse boundary method. Please.
Okay. So it was all in the title. So we present a novel framework for the fluid structure interaction based on the immerse boundary method. With this approach, the solid is embedded inside the fluid domain, and the contribution of the solid is included as a source term in the Navier-Stokes equation. We couple two different discretizations, finite differences for the fluid and finite elements for the solid. And in particular, what we discuss is a parallel and efficient implementation of the L2 transfer between the two domains, and we apply our method to describe self-induced oscillating deformations of an elastic beam in a fluid channel.
Thank you very much. Next one is Jan Zapletal from IT4 Innovation Ostrava, boundary element quadrature schemes for multi and many core architecture. Please.
Okay, thank you. Morning, everyone. In this poster, we present our experience with the implementation of boundary element quadrature schemes for modern many-core processors, especially of the Xeon Phi family. And we present scalability experiments, not only with respect to the number of OpenMP threads for these many-core CPUs, but also with respect to the width of the SIMD register, which is getting increasingly more and more important for scientific codes. And we, of course, also describe the optimization that one has to do to get these nice results. So if you are interested, then I'd like to welcome you at the poster site. Thank you.
So you can stay there because I think the next poster is still yours. Yes, energy efficient high-performance computing due to application dynamism. Please.
Correct. This is a very, very different topic. In this poster, we summarize recent developments within the REDX project, which is a Horizon 2020 project which aims at efficient utilization of HPC hardware resources from the perspective of energy consumption. And we are developing a tool suite which can analyze your application, and then within the runtime of the application can dynamically change the hardware and runtime parameters of the system so that the application runs efficiently. Again, if you're interested, I'd be happy to see you at the poster site. Thank you.
Thank you very much. Next one is Simon Bauer, LMU, efficient on-the-fly operator assembly for HPC finite element codes. So please.
So, good morning, everybody. Recently, we proposed a novel approach for an efficient finite element stencil assembly on curved domains. Now we extended it to more complex systems of PDEs, including variable material parameters. And compared to a traditional implementation, we achieved a performance improvement by a factor of about 20 and a parallel efficiency of more than 90% on up to 50,000 API processes. With this approach, we were able to run a geophysical application with realistic input data for a system with 10 to the 12 degrees of freedom in a couple of minutes. And if you're interested in details, I'm looking forward to meet you at my poster. It's poster number 6.
Thank you. Yeah. Alberto Madonna, CSCS, flexible and high-performance stencil codes with grid tools for PI.
So my poster introduces Grid Tools for Pi, which is a Python package meant to assist in the development of efficient stencil codes. Grid Tools for Pi provides a series of high-level abstractions that hide many of the complications associated with writing stencil programs and lets the user focus on just the definition of the mathematical operators. At runtime, specific code is generated for different backends targeting, for example, debug or performance using the Grid Tools C++ libraries. And if you're interested, I can showcase a couple of Jupyter notebooks during the reception this evening. Thank you.
Thank you very much, Alberto. Next one is Demosthenis Pasadakis, UZI, Fluid Structure Interaction Simulation of the Human Heart. Please.
Hello, everyone. My name is Demosthenis Pasadakis. And I'm a master's student of the Institute of Computational Science at UZI. Our goal, together with Dr. Nestola, Dr. Mafesanti, Professor Krause, and our collaborators from the University of Bern, Barna Becek, and Professor Obrist, is to perform fluid structure interaction simulations of the human heart during the diastolic phase of the cardiac cycle. In order to do so, we develop patient-specific geometries based on segmentations obtained from CT scans, employ a fictitious domain method, and run our simulations at CSCS speed-stained supercomputer. Glad to see you later if this is of interest to you.
Thank you very much. Next one is Andrea Arteaga, Meteo Swiss, model-driven choice of PDE numerical solvers, please.
Good morning. How do you choose the numerical methods to use for the solution of a particular problem? Usually people tend to use something based on the bias due to personal experience or code to reuse. We wanted to get rid of this bias and to propose an optimization strategy, which is given in the gray area in the middle. We identify the options which could be used for our problem. We perform accuracy modeling and performance modeling, and we optimize based on a constraint like accuracy and minimizing the runtime, for instance. We have some results here, and we have some more if you join us in the poster number 9. Thanks.
Okay, thank you. Axel Übel, HZDR, Open Science with Open MPMD, please.
Hello. I brought you my USB stick. My USB stick is scientific data. I want you to ask, if I vanish here in 30 seconds, what would be your first question if you get this USB stick? That's what my poster is about, because it's the same question that you asked when you get an HDF5 file. What's the unit in there? What's the time scale? What's the scale in general? Well, if you want to describe this better and want to change that, then come to my poster about OpenPMD.
Thank you very much. Next one is Lorenzo Fabri, USI, efficient and portable MPI support for approximate Bayesian computation, please.
Good morning, everybody. The contribution of this project is the development of a parallel backend based on MPI for ABCPy, which is an open source library for approximate Bayesian computations written in Python. We also provide the analysis of scaling properties, which was performed on the CSCS supercomputer PASC17. If you want to know more about the interesting results we got, just come to our poster. Thank you.
Thank you very much. Next one is Saeed Mirazimi, SFU, parallel immersed boundary simulation of worm-like swimmers in the inertial flow regime. Oops.
Yep.
And I messed up, sorry.
Yep. Here we present some of our results of simulations of worm-like swimmers in inertial flow regime. So with worm-like swimmers, we're talking about nematodes of length scales of millimeters. And we're mostly interested in intermediate Reynolds numbers. So if you would like to chat about fluid dynamics, CFD, fluid structure interaction, and immersed boundary methods, and anything else such as grad life in Vancouver, Canada, just stop by in the evening. Thanks.
Thank you very much. Next one is Rodrigo Pinto Coelho, USI, parallelization of graph partitioning using Metis and OpenMP. Please.
Good morning. In my project, we studied different ways of parallelizing Metis. Metis is an open software package designed to find optimal partitions in graphs. And why is that important? Graph partitioning can be used to find field-reducing orders in matrices, design of very large-scale integrated systems, and load balancing in supercomputers.
Thank you very much. Next one is Dananyai Toma USI, pruning highway networks. Please.
So deep learning is all hype these days for significantly improving state-of-the-art results on various tasks across various domains. Given the interesting tasks that neural networks can perform, they are increasingly being used in applications designed for mobile devices. But over the years, as neural networks have gotten better, they've also gotten a lot bigger, which makes them difficult to run on mobile devices. In this work, we propose a new approach to reduce the size of the network, and we are able to reduce the size of the network by up to 85% without much loss in accuracy. Thank you.
Thank you very much. Next one is Keen Mariotti, CSCS, shifter experiences with high-performance containers. Please.
Morning, everyone. We realized that building and maintaining HPC applications is hard. For example, just think about the fact that on the HPC system, usually you don't have the package manager that you can use to install the dependencies of your software. So our solution to the problem is to use containers. Basically, we take the scientific application, the dependencies, we put it in the container, and then we can run that container on different systems, and we get native performance.
Thank you very much. Okay, next one is Vaclav Apla, IT4 Innovation, again, Ostrava, solving large-scale quadratic programming problems with Permon. Please.
Dear children, I will tell you a story. Once upon a time, cute little tiny dwarfs called Permons from dark and deep Czech coal mines produced a special mixture of quadratic programming, PETSI, and domain decomposition methods. It turned out to be useful for many things, such as contact mechanics, support vector machines, and time series clustering. So come and see.
Okay, thank you. Next one is Toby Simpson, USI, load balance partition refinement with the graph P Laplacian. Please.
Hello. Graph partitioning is one of the fundamental problems of scientific computing. We optimize in a p-norm and solve an eigenvalue problem in a nonlinear graph P Laplacian operator consistently improving quality over state-of-the-art methods for graphs with up to 100 billion edges. Thank you.
Thank you. You were ultra fast. Sebastian Kuckuck, whole program generation for complex fluid flow solvers, please.
Hello everyone. So this poster is about geometric multigrid solvers for the Stokes and Navier-Stokes equations. And if you have implemented these, you probably have come to the point where you wanted just to write your discretization in your solver in an abstract fashion and still wind up with high-performance code. This is exactly what we do with our domain-specific language, AccessLang, and our code generation framework. We produce this code, and as a bonus, it is automatically parallelized using MPI, OpenMP, and or CUDA, and some automatic performance optimizations can be carried out as well. So if you're interested in having a look at how we specify this in our language, please come by my poster and we can talk about it. Thank you.
Thank you. Next ones are posters in emerging domains in HPC and engineering. So first one is Maxim Vision, UZI, scalable MCMC algorithm for the accurate estimation of exponential random graph models. Please.
Thank you. So maybe the first one, but maybe also the last one in this session. So we have developed, so our results maybe if you are working in the data, with data, and if you analyze data, then you can find our results very interesting. So we have developed scalable Monte Carlo algorithm for maximum likelihood estimation that can be used in, I think, many fields of science, and it's very general, and you are welcome to, if you have more interest in it.
Thank you. Next one is Sebastian Leguizamon, I hope it's correct, EPFL, a multi-scale model for the simulation of sediment impact erosion of metallic targets. Please.
Thank you. In our lab, we're interested in the process of erosion of hydraulic turbo machines. The problem with simulating this process is that it's inherently multi-scale. It means that it involves many orders of magnitude in both time and length scales. We have therefore developed a new multi-scale model to tackle this problem. We solve the sediment impacts on the one hand on the micro scale, and also the sediment transport on the macro scale. And by coupling these back together, we're able to solve an otherwise intractable problem. Thank you.
Thank you very much. Next one is Siamak Ali Mirzadzadeh, EPFL, GPU Spheros, a GPU accelerated versatile solver based on the finite volume particle method, please.
Good morning, everybody. So Spheros is a CPU version of a software, is a 3D solver. It's in order to simulate the fluid flow and also sediment transport and the interaction between silt and solid. So we switched to GPU to more accelerate to further speed up the software, and we designed from the scratch. So we compared Tesla P100 with new Intel CPUs. So you can come to see the results. Thank you very much.
Thank you. So next posters are in life sciences, and the first one is Barna Beksek, University of Bern, aortic valve hemodynamics using variational transfer immersed boundary method, please.
Okay, good morning everyone. We're presenting our FSI simulation tool that we've developed in collaboration with UZI by coupling high-performance libraries in this semi-weak fashion where we do fixed point iterations in each time step. We've validated it with common FSI benchmarks, and our goal is to apply it, or we are applying it to aortic valve flow. And you'll hear more about our efforts in porting parts of this on the GPU by our collaborator, Hadi.
Thank you. Next one is Davide Garolini, University of Zurich, Kampa R1, an R package for extracting metastable states from time series data. Please.
Hi everybody, I'm Davide, and I will present Campari. That is an R package that will be like a Swiss Army knife for your time series. And if you come by my poster, I will show you how you can easily find metastable states and build Markov state models on your time series. And I will show you its application in hydrology data and neural networks, neural data set, and please come.
Thank you. The next one is Gianvito Grasso, ITSIA, elucidating the effect of polymer flexibility, molecular geometry, and charge neutralization of siRNA polycation complexes, free energy landscape, a computational study. Very good.
Good morning. The purpose of this work is to evaluate the interaction between the RNA and low molecular weight polymers because of their application in gene therapy. And computational simulations have shown several differences among polymers in terms of polymer binding site and affinity. And results of the present work have several implications for what concern the design process, the future design process of polymer in order to finally reach the best compromise between complexation stability and releasability of the delivery system. Thank you.
Thank you very much. Next one is Hadi Solfagari, University of Bern, flow stability and transition passed on an aortic valve using a hybrid multi-core, many-core, massively parallel Navier-Stokes solver. Please.
Good morning. We aim at understanding the instability mechanisms in the aortic valve system using a hybrid multi-core, many-core, massively parallel Navier-Stokes solver. A range of instabilities are shown for both mechanical and bioprosthetic-like setups. Or MPI version of the flow solver is written in Fortran, and we used CUDA-C to port the computations to the Pascal GPUs. And thank you.
Thank you very much. Okay, next one is Cassiano Langini, University of Zurich, focused diversification of biomolecules for drug discovery by progress index guided sampling. Please.
Morning, everyone. How much time have you spent in front of your computer waiting for something to happen in your molecular dynamics simulation? And nothing did. That's what happened to us. We have simulated that protein over there, bromodomain, for a total amount of 90 microseconds. And we were able to find only 2 states. But this was not enough for us. We had other questions to answer. We wanted to understand which were the independent motions of the 2 loops over there. We wanted to explore efficiently the phase space of this protein. And so if you're interested in understanding how we did this without a collective variable, you should come to my poster.
Thank you very much. The next one is Stefano Ragnolo, USI, Funnel Metadynamics 2, Graphical User Interface and Implementation in Plumet 2. Please.
Good morning. I'm a PhD student in the group of Vittorio Limongelli at USI. In my poster, I present a graphical interface to run in a user-friendly way the funnel metadynamics, which is an innovative method to study protein ligand binding. This interactive interface has many options that the user can use to prepare and analyze the data from the simulations. With this tool, this tool allows one to obtain the binding modes of the ligand and an accurate estimation of the absolute binding free energy. Thank you.
Thank you. I think this is the final posters in physics, and the first one is Andreas Flüglistaller, University of Geneva, formation of solid H2 in the ISM. Please.
Hi, I'm studying computation instabilities of fluids with phase transition. This can lead to solid H in the ISM, for example. And in order to do this, I'm using molecular dynamics, but usually in molecular dynamics, you get a few femtograms, a few milliseconds. I need years, I need many kilograms, so we are not using supermolecules, which each supermolecule has a big number of molecules. Thank you.
Thank you. Next one is Kirill Pakruski, ETH Zurich, non-abelian fractional quantum Hall states and topological quantum computation, please.
Hi everyone, I have a post about topological quantum computation, which is an approach to quantum computation protected from errors by construction. I'm simulating something which can eventually become a qubit. On my post I have information about the physics behind, about our results and about the classical computation we do on PISDEN to simulate the things. So no matter your background, there is no excuse for you to skip this poster. I will see you there.
Thank you very much. Next poster is Aaron Scheinberg, EPFL Lausanne, Numerical Method Optimization in Particle in Cell Gyrokinetic Plasma Code ORB5, please.
Hi, my group at the Swiss Plasma Center in Lausanne works with a particle and cell code to study plasma physics inside of tokamaks, which are the most promising avenue forward for fusion energy in the near future. This particular project was about implementing OpenMP multi-threading as well as changes to our arrays and modules with the aim of speeding up the code. The great thing about that kind of project is that knowing how many millions of node hours we use, I can estimate how much improvement we got and compare that savings in resources with the salary of a postdoc. So come and find out if it was worth it.
Okay, thank you. Next one is Flavio Calvo, IRSOL, the linear polymerization of the solar continuum radiation from numerical simulations of the solar atmosphere, please.
Hello, we used numerical simulations, high-resolution numerical simulations of the solar atmosphere that we carried out at CSCS in order to compute polarization maps of the sun. Actually, those polarization maps are synthetic observations. They can be compared directly with observations that we also carried out at our institute, Solar Institute for Solar Research in Locarno. And in particular, we computed the variation of linear polarization from the center of the sun, of the solar disk, to the limb. And it agreed pretty well with the observations. I just note that it might well be that the only sun that is visible today and tomorrow is probably synthetic and in our poster, so please come and have a look. Thank you.
Okay, thank you very much. I think we're finished. I hope that you all will participate to the poster session at 7 p.m. There will be also a reception there, and that there will be staff from the PASC conference distributing something for you to vote. So please do vote. Thank you very much.